So what we want to do is we basically want to come up with a more systematic way of solving for these. This is a challenging section that hopefully you'll pay a lot of attention to because you're going to be using this every day in mechanics and materials. Plus, it's the basis of all structural engineering. Okay? If you ever wanted to redesign the beams of your house, or you wanted to know if you could tear a wall out, this is how you know. This is how you do it. So it's pretty cool. We're going to learn about the relationships between distributed load, shear, and moment diagrams. We're going to use the method of integration to determine the shear and moment diagrams for a beam. The proofs are meant to give you the relationships that you need to do these. It's very important that you follow along and you understand what I'm doing. Otherwise, you won't know some of the subtleties of how these work. So look up here and just try to picture cutting that little piece out of this beam right here. We're going to cut that piece out of this beam just like we've been cutting in Chapter 7. And we draw the shear on one side. And notice how that's pointing up, which would be positive for drawing the right-hand side. We have the moment. The moment would tend to turn the edge up into a smiley face. So we're following our sign conventions. The only difference between this and what we've cut before is we're cutting two sides. So you see a shear here and a moment. And then over here, you see another shear and a moment. Now, those aren't going to be exactly the same. They're going to be a little bit different. So this one's labeled as shear. This one's labeled as shear plus delta shear. In other words, shear plus a little bit more shear. Okay? Because we know that it's not exactly the same location, but it's pretty close. This one's labeled moment. That one's labeled moment plus delta moment. Moment plus a little bit more. It's going to be a little different. The width of this is delta x. You guys can see the calculus coming in, right? So the width of this is delta x, meaning a small change in x. Then on top, you notice that we cut this out underneath a distributed load. You can see this dotted shadow here. That is the distributed load that would exist on top of just this portion of the beam. But then what they're doing is they're combining two steps. They're saying that's the distributed load, but I can replace it with a point load. The magnitude of that point load is going to be the area of this shaded region. Now, this isn't exactly a rectangle, but we're going to treat it as if it were a rectangle because we're going to get smaller and smaller delta x until the difference doesn't even matter. Okay? So if we treat it like a rectangle, we just need base times height. Base is delta x. Height is wx. So change in force is equal to wx delta x, which means the magnitude of that is wx delta x. Okay, here's the most confusing part. We would have to know where this is located on the beam. If it was a triangle, where would it be located? 1/3 from the longer side. But we don't know what shape it is. So we're just going to use a constant. This is k. I know it's hard to see there. This is k, and that's delta x. So it's saying some fraction of delta x. We don't know what fraction. We don't really care. If it was triangle, that would be k would be 1/3. If it was something else, it would be something else. Now what we're going to do is just what we've done before. This is a free body diagram. I'm going to start off with sum of the forces in the y direction is equal to 0. I have on the left-hand side, I have a shear. On the right-hand side, I have a shear plus delta shear pointing down. So I've got to put that as negative because I'm doing a positive y direction. And then I have to add the force on top, the distributed load that we turned into a point load. And that is going to be pointing down, so it's negative. And the magnitude of it is the height times the base. Okay, once I have that, all I have to do is do some algebra. I'm going to go ahead and put that negative sign inside, and we get shear minus delta shear minus wx delta x equals 0. Notice that these two cancel, and we end up with negative change in shear. It's going to be equal to wx delta x. And then I'm going to divide both sides by delta x. We end up with, I'm going to put the negative on the other side, and we end up with delta shear over delta x is equal to negative wx. Now, of course, we made some simplifications, and those simplifications are only valid if our delta x is really, really small. We can actually take the limit. If we take the limit as delta x approaches 0, what will delta x over delta v over delta x, what will that turn into? So on that side, instead of it being rise over run, instead of it being average slope, it turns into instantaneous slope, dv dx. The derivative of shear with respect to x, also known as the slope. That's going to be equal to negative wx. This is a mathematical equation, and it's also a relationship that we can use to make our own shear and bending moment diagrams. So we want to use it for both. Don't forget of it as an equation, but also let's put some words to it. What is this side? What's dv dx? What is it graphically? If I had a shear diagram, what would it be on that diagram? Be the slope. The tangent to the slope would be the same thing. Yeah. So this is slope, or instantaneous slope, of shear. And I'm saying it's equal to wx, which is the value of distributed load. And notice that there's a negative sign there. The negative sign is because the arrows are pointing down. Okay? When the arrows are pointing down, we don't make our shear go down. Our shear is still going up. So that negative sign needs to be in there. If those arrows from this derivation, if they were pointed up, the negative wouldn't be there. That's why it's really important you understand the derivation and know when to use the negative and when not. Okay, so that's the first relationship. I'm going to introduce you to 6 relationships today, all of which you're going to be using to make shear and bending moment graphs. All right, same exact slide, but we're going to do moment now. Same exact slide, same exact setup. We're going to do some of the moments about point O. You can see point O is down there on the right-hand side of the cut. We do some of the moments about point O. You're going to have negative m. That comes from the left-hand side. You notice it's in the negative direction. Our typical positive going this way. And then we have to add on to it m plus delta m, which is the moment on the right-hand side. Then we have to add on to it the moment caused by the shear force on the left-hand side, which would be a negative shear times the distance, which is delta x. Okay, one more force that would create a moment, and that's that top force, the point load. The magnitude of that point load, it's going to be a positive moment. The magnitude of the point load is wx times delta x. And the distance from O is that constant k multiplied by delta x. So that comes from right here. Basically what it's saying is we don't know the shape of the distributed load. So when we put a point load there, it's not going to act right in the center. It's going to act some distance from the side. K would be a third if it was a triangle. But we don't know what its shape it is, so it's just a constant. Okay, so now we see that the m's cancel, and we get delta m equals, put everything on the other side, that changes the sign, v delta x plus wx minus wx delta x k delta x. Or I'm just going to put k over here, delta x squared. Now I'm going to divide by delta x on both sides, just like I did before. And we end up with change in moment over change in x is equal to shear minus k wx delta x. Now we're going to take the limit as delta x approaches 0. As delta x approaches 0, delta m over delta x becomes dm dx, the instantaneous slope of moment. On the other side, shear doesn't change, but what happens to this term? It goes to 0. As delta x gets smaller and smaller and smaller and smaller, that term means less and less and less and less. Okay? So we end up with dm dx equals shear, which is exactly the same relationship we had between the loading function and shear. We have that same relationship between moment and shear. What's that relationship? This is the slope of moment, and this is the value of shear. That's 2 of the relationships we need to remember. I'm going to give you 2 more, and they come from the exact same equations. So I'm going to go back to the previous slide. We have the slope of the shear equals negative wx. All I'm going to do is take dx and put it on the other side. If you ever see an engineer doing this, they're about to integrate. because that's how we do things. So I have a dv on one side, a dx on the other. I integrate both sides. I'm integrating in terms of dv here and in terms of dx. So I need my limits of integration. I'm going to start with my initial shear. I call that v naught, and go to final shear, which I'll keep as a variable v. The next one is going to go from 0 to x. On the left-hand side, that's just shear minus initial shear. So I'm taking the integral of dv. On the right-hand side, that's the integral, negative integral from 0 to x, wx dx. Or change in shear is equal to the opposite of the integral from 0 to x of wx dx. This is another relationship. On the left-hand side, we have change in shear is going to be equal to, what is the right-hand side graphically? Area under the curve. Good. The change in shear is equal to the area under loading curve. Now, we kind of knew that one already, right? We've been taking areas of triangles and stuff to find the point loads, and that's just basically what it's saying here, is that the change in shear is going to be equal to the area under the loading curve. Keep in mind, this is a mathematical equation we can use to derive the actual equations. It's also a relationship we can use to draw our diagram. Same exact path here. dm equals shear dx. Integrate both sides. This is from initial moment to final. This is from 0 to x. So we get m minus m naught equals the integral from 0 to x of shear dv. The only difference here is there's no negative sign. Okay? Once we have the shear, there isn't a change in sign between the shear and the moment. There is between loading and moment just because the arrow is pointing downwards. Okay? And that means the change in moment is equal to the area under the shear curve. Okay, 4 relationships so far. Any questions about those? All right, 2 more. These ones are kind of the ones we already knew, or at least we have hinted at in the past. Okay, so now we have a point load instead of a distributed load. Everything else is the same. I'm just going to go ahead and do sum of the forces in the y direction. We get shear minus shear plus delta shear. Nothing different there, but then just minus f equals 0. Shear minus delta shear equals f. These two cancel. Change in shear equals negative f. And what that's telling us, at a point load, the change in shear equals the value of point load. So this is a jump. In other words, a discontinuity in our plot that is equal to the value of that point load. We're going to do the same thing on the next one. The only difference is instead of a point load, this is a couple moment. This is a moment applied to the beam at that location. We're going to do the sum of the moments equals 0. M, negative m plus delta m. The way that this one's currently drawn is clockwise, and that's important to remember. This moment's drawn clockwise, so I put it as negative m naught, which is that applied couple moment. And then we have to add on to it negative shear times delta x. Same thing we had before, the moment caused by that shear. That's all equal to 0. The moments cancel out, and we get delta m is equal to moment. Notice it's positive with a clockwise moment, plus shear times delta x, but we have the same thing as before. As delta x approaches 0, that term is going to disappear. And we end up with the change in moment is equal to the value of the couple moment. This might seem like pie in the sky right now, but it's really important to understand those relationships. And now we're going to use them to actually create some shear and bending moment diagrams. Okay, so what we're going to do using these relationships. The first step has not changed. We still need the support reactions. So first step, what I've been calling step 1 for 3 chapters now, is to find support reactions. Okay, then we're going to section the beam at every general location x where the loading changes. And we're going to determine Wx for each section. Okay, so what that means is we have to look at the distributed load and find the areas where there's an equation for the distributed load. This could mean a straight line, it could mean a curve, it could mean whatever they give us. But for each section where the loading changes, we're going to need a different equation. And then we integrate. We integrate negative Wx, and that gives us shear. We integrate shear, that gives us moment. Then we use boundary conditions for each region to determine the integration constants. That's very important. The integration constants are not always going to be 0. We're not always going to start at x equals 0. Once we go along the beam, whatever the initial x is where that loading function starts is what we put in for the limits of integration. I'll show you a more concrete example of that later. Then we draw our diagrams right under the free body diagram of the beam. This is example 7-55. We want to draw the shear and bending moment diagrams. For step 1, we're going to solve for the support reactions. I'm going to do that over here. I'm going to replace the distributed load with a point load of, looks like 1,000 pounds. Okay, sum of the moments about point A is equal to 0. Okay, so By is 510. Then we're going to use the sum of the forces in the y direction is equal to 0. Ay equals 490 pounds. That's all just step 1. Once you have step 1, you're going to draw a free body diagram, and you would do this in a different spot on your paper, but I'm just going to go ahead and add it to the top of this so I can use the same slide. My Ax is 0, sum of the forces in the x equals 0. And my AY is 490. My BY is 510. That's how you always want to start off. And I'm going to go back and I'm going to turn my point load back into a distributed load. And now I want to do this one 100% using relationships. We'll do the next one using the actual integration. Okay? So we need to use those relationships we just learned. I'm just going to start by drawing the shear. Okay, the very first thing that happens is what? What's on the left-hand side, the first thing we see? Very good, a 490-pound point load. And the 490-pound point load, we need a relationship that relates point load to change in shear. Yes, thank you. Pounds. Okay, so that relationship was right back here. A point load is equal to a change in shear. If that force is pointed downwards, we expect it to jump down. If it's pointed upwards, we expect it to jump up. So this one, in this case, is pointed up. So we expect the change in shear is going to go from 0 to 490 pounds because of that point load. For the next part, we have a distributed load. The distributed load is our loading function Wx. What is the equation of the line for our loading function? 0 is less than x, which is less than 20 feet. What is Wx? Straight line, not too hard. 50 pounds per foot. Good. We have a relationship that tells us in a distributed load, this is the distributed load, we have two relationships. The value of the distributed load is going to be equal to the slope of our shear. That's the first one. So what's the slope of our shear? Negative 50. The negative comes from that negative value here, and Wx is 50. We also know the change in shear is going to be equal to the area under the loading curve. So I'm going to go back over here, and I'm going to say, okay, well, the change in shear is the area under my curve. What is the area, what is this green area under the curve here? Change in shear, good. So the equation that I'm going to use is change in shear equals integral from 0 to 20 of Wx dx with a negative. So if I can take that, the area under that curve, it's just 50 pounds per foot times 20 feet. The area under that curve is 1,000. It's negative 1,000 because it's pointing down. So I'm going to go from 490, 1,000 down, so that I'm at negative 510 pounds. What's my slope? Negative 50. Okay, what happens next? I have a second point load, right? What do I do with the point load? I jump up. I jump up from negative 510 to 0. And then the rest of the way there are no forces. Okay, notice how I'm labeling the important points. This one I would make sure to label as 20 feet. This one I would label as 30 feet. And then I'd have to figure out what this point is in the x-axis. How would I figure that out? I know my slope, right? Yeah, so my slope is negative 50 times x. And I know that has to be equal to negative 490 when I get to the x-axis. Solve for x. X is equal to negative 490 over negative 50. So that's equal to 9.8. So this would be 9.8 feet. And I just want to stress, notice I'm putting 9.8. I'm not putting 10 and making me guess that it's right a little bit before 10. I don't want ranges, I want exact numbers to show that you know what the math is. Okay, so there's my shear plot. That was easier, right? Now we're going to do moment. Moment will be in foot-pounds. We always start at 0. In the last one, we started at 0, and then we had a point load, so we jumped up. Is there a couple moment on the left-hand side? No, so we don't do any jumping. We start at 0. But then we need to figure out where we go from there. And the equations that we're going to use are these ones. The slope of the moment equals the shear. The change in moment is equal to the area under the shear curve. So what's my initial slope? What's the value of the shear at 0? 490. So my initial slope is 490. I don't really know what 490 looks like, but I'm going to guess it looks something like that. I know it's up. I know it's probably steep. When I get over to here, when I get to there, what's my slope? When I get to 9.8 feet. 0. My slope is 0. So I'm just going to make a little tangent line at 0. So I can start to already picture what my moment's going to look like. Okay? Then I have to figure out how much moment has changed. So I know the moment's going to do something like this, because the slope starts out really steep and then it goes to 0, because the slope of my moment is equal to the value of my shear. But I don't know what the value is on top. How I find that out is the second one. The change in moment is equal to the area under the shear curve. So I need this area. So that would be the area is going to be 490 pounds times 9.8 feet times 1/2, because it's a triangle. 2,401. So that's this value right here. 2401 is where it goes to. Then I'm going to look and figure out what this is, the second green area. So I'll call this area 1, call this area 2, is going to be equal to 510 is the height. The distance is going to be 20 minus 9.8. And I need that 1/2 because it's a triangle. Okay, so that is equal to 2601 foot-pounds. Okay, what that means is between 9.8 and 20, the change in moment is 2601 foot-pounds. Okay? So where is it going to be at 20 feet? Negative 200. Negative 200. What's the slope going to be? Negative 510. Negative slope looks kind of like that. The slope is 0 up here, so I connect the two. Okay, what's the slope after that? 0. And then what happens at the end? I have a concentrated moment. So I jump. Do I jump up or down? Up. I said clockwise is positive jump. So I jump up and I'm back to 0. That's the way that you check your work. You always start at 0, you always end at 0. Okay? This is going to be 20 feet here. This is going to be 9.8 feet. Notice how powerful this is. We were able to create the shear and bending moment diagrams for that beam without even doing calculations. We found a couple areas and stuff.